One of the applications of all of this are basic motors. And obviously motors are around us all the time, so this is a nice application, something that takes everything we're studying and relates it back to something that you experience every day. So this is a very basic motor. This is the simplest motor we can talk about. A real motor, if you went and took apart someone's Tesla fancy car, they're going to have a much fancier motor than this. However, this gives you the idea of how it works. So notice that we're going to have some magnets, and on the next slide I'll talk about the components in detail. They're creating a magnetic field. We have a loop in the magnetic field. Now notice that it's not a perfectly closed loop, and the reason for that is that if I have a loop like this and I say, there's a current flowing, well, a really good question would be, well, why is a current flowing? Is there a potential difference across it? And if so, where is that battery? So frequently we show loops this way, but this is really ideal. And you can't just start a current and have it continue indefinitely if there's any resistance. So in this case, we're actually going to show the current being caused by a little battery. And we have our current flow. And just as we talked about in the previous video, there's going to be a torque if it is not aligned with the magnetic field. So you can see that this is at some angle, so therefore there's going to be a torque which causes it to rotate. But now there's a problem. So we said that there's a stable equilibrium when, this is your edge view, your magnetic dipole moment aligns with B. If you have that, your torque equals 0 and we say it's at equilibrium. So this rotates through. At some point, it would reach this point. After that point, it would actually be driven back to this. So effectively, your motor would sit there and really just kind of oscillate back and forth rather than rotating around a full circle. That's not very useful. Having your motor just go back and forth a couple of degrees doesn't make your car tires spin in any useful way. So we need to do something that's going to fix this. Now, one way is that you only allow current to flow half of the time. So basically you have current flowing so that you have a torque like that, and then here you just have basically momentum carry you through. There's not actually any torque, but then you get here and you have your torque again. So that's one simple way to do this, but it's not very efficient. And whatever friction you have is going to slow it down and possibly you won't make it back around. So there's a magical little device called a commutator. And what the commutator is doing, and it's a little tricky to see in this picture, but you see that there's this little gap here and a gap there that you can barely see. The commutator is what's making the electrical connection between the battery and this loop. So the loop doesn't continue out to anything, it's just making the connection here. And it's actually split in the middle so that as the loop flips over, as it goes through, say, this critical point, your current actually switches direction. So in one direction, you have current this way, but then as your loop rotates around, your current is now going the other way. And all that's happening is that this part of the loop stops touching that side of the commutator, which is connected to the negative side of the battery, and it starts touching the positive side of the commutator, connected to the positive side. So this is basically flipping the direction that the current is flowing as it's switching from one half of the rotation to the other. So in that case, you then never have a stable equilibrium. It is always having that torque push it through, and you don't ever end up with oscillations. So this is tricky to think about, and again, I'm going to try to break down the basic components of this picture. So there have to be some sort of external magnets, or even one magnet. Now for our situation, we would want to think of this as a uniform magnetic field because then we can calculate it easiest, but it doesn't have to be a uniform field. So uniform field is easy for us, but your motor will work even if it isn't. The loop of current is what is actually rotating, and there's a torque that is due to the current interacting with that external magnetic field. So keep in mind that we don't care about the magnetic field that the loop itself is making. Sure, there is one, doesn't matter. The commutator is really the key ingredient, which is changing the direction of the current flow so that there's always a torque causing the loop to rotate, and there's never a torque slowing it down. And again, all the commutator is basically this split piece of metal that allows the current to flow one direction and then the other one. So do think about this. The last thing about this picture is that we haven't shown a load. Like if you really think about this, you might say, well, why do I care about making this little loop spin? You said this is a motor, but this seems completely pointless. And you're right. What's shown here is pointless because we haven't shown the load. And the load, for instance, is going to be the axle connected to wheels. Maybe it's directly connected to wheels, or maybe it's connected to a pulley and this is driving, for instance, an elevator or something like that. So the idea being that we need these three things to make something spin. And we have the basic idea of a motor, but then we attach it to something we want to make spin. So we could, for instance, put a wheel on the back end of this or something like that. Now, we haven't shown that here because here we're just trying to think about the magnetic fields and forces and torques going on here, and the presence of a wheel doesn't change that. So understand that that's how we make this useful. And again, the three key ingredients are loop, external magnetic field, and commutator, which again has this voltage source causing the current.